A perfect square is created when a whole number is multiplied by itself. Similarly, a perfect cube is formed when a whole number is multiplied by itself 3 times. Now let's look at the opposite operation, the square root. We will find the square root of 16. We can rewrite 16 inside the radical as its identical factors, 4 times 4. The rule of square roots is that a pair of identical factors inside can be brought out as a single representative value outside. So, the pair simplifies completely, leaving just 4. The exact same principle applies to cube roots. Let's solve the cube root of 27. We factor 27 into 3 identical parts inside, 3 times 3 times 3. Because the index of the root is 3, we now look for groups of 3 matching values. This whole triplet group collapses into a single 3 outside the radical container. Now let's look at how to find the square root of larger numbers. Like 225. Using prime factorization, we start by breaking 225 down into any 2 factors. For instance, 9 times 25. Neither of these are prime yet, so we continue. 9 breaks down into 3 times 3. And 25 breaks down into 5 times 5. Now that we have reached prime numbers, we circle all these bottom children nodes. Gathering these primes together, we can write 225 in exponential format as 3 squared times 5 squared. Now, let's rewrite our original problem, the square root of 225. Using our prime base, we substitute 225 to rewrite it as the square root of 3 squared times 5 squared. The square powers perfectly match the radical, meaning we can bring out one representative factor for each group. This strips away the radical house, pulling out single factors, 3 times 5. Finally, we multiply them out to get our fully simplified answer, 15. Let's find the lowest common multiple and greatest common factor of 24 and 36 using prime factorization. First, let's break both numbers down into their prime factor trees to gather their terminal leaves. Writing them in exponential format, 24 becomes 2 cubed times 3. While 36 becomes 2 squared times 3 squared. To see their relationships clearly, we can arrange every single individual prime factor inside an alignment grid column table. Let's group the columns. Green boxes show factors that both numbers share completely, while purple boxes show individual factors that belong exclusively to only one of the numbers. To find the greatest common factor, we look only at columns where both numbers share a factor. Multiplying 2 times 2 times 3 gives us a greatest common factor of 12. For the lowest common multiple, we pull down a representative from every single column, multiplying all shared and unshared elements together. Doing this yields an LCM of 72.